To achieve a perfect score in high-performance computing, you have to abandon sequential logic. Writing code that executes one instruction at a time is a habit you must break. You have to replace it with a parallel computational mental model, shattering single operations into thousands of simultaneous threads. We are ignoring low-probability textbook fluff. By analyzing 6 years of university exam papers, we can isolate exactly what is required to construct a mathematically guaranteed 70 out of 70 marks. That perfect score relies on mastering 4 interconnected pillars of the HPC stack: network topology, performance scaling, hardware architecture, and algorithmic design. True parallel execution requires all 4 layers to function together. An optimized hardware topology means nothing if your scaling math is flawed, or if your software algorithm creates a single-threaded bottleneck. The baseline problem in any parallel system is physical communication. When one source processor computes a value, it has to physically transmit that data across the network to every other processor without creating massive latency delays. The standard exam proof for this is the 8-node hypercube. It is a 3-dimensional structure where each node is labeled in binary, from 000 to 111. 2 nodes are directly connected if and only if their binary labels differ by exactly 1 bit. To execute a one-to-all broadcast on this structure, we use a mechanism called recursive doubling. At step 1, the source node 000 sends the message across dimension 0 to node 001. The number of informed nodes doubles at each step. At step 2, both informed nodes send data across dimension 1 to node 010 and 011. At step 3, all 4 nodes send across dimension 2 to the remaining 4 nodes. A 3-dimensional cube requires exactly 3 steps to reach all 8 nodes. This gives us the foundational communication cost formula. Total time equals log base 2 of p multiplied by the quantity ts plus tw times m. This equation separates the hardware limitations from the message size. TS is the physical startup latency required to initiate the link, and TW is the per-word transfer time, multiplied by your message size M. But the physical hardware is only half the equation. You have to interface with it using software, specifically the Message Passing Interface, or MPI, and you have to choose between blocking and non-blocking communication. If process 0 and process 1 simultaneously call a blocking MPI send to each other, neither function returns until the message is received. Both processors wait forever in a deadlock. MPI iSend solves this by initiating the transfer in the background and returning immediately, allowing the CPU to execute computation-communication overlap. An optimized hypercube network is entirely wasted if your software protocol blocks the CPU and forces it to sit idle waiting for data transfers. You might assume that doubling the number of processors cuts execution time in half. The strict mathematical reality is that efficiency, which is speed up divided by the number of processors, almost never equals 1. The system degrades due to 5 sources of parallel overhead, the 2 most punishing being inter-process communication and synchronization delays, where processors sit completely idle waiting for a barrier lock to clear. This balance is governed by granularity, the ratio of computation time to communication time. Low granularity means your processors spend more time talking to each other than actually crunching data, which ruins system performance. Look at this graph charting speedup versus processor count. Amdahl's law proves that if your problem size is fixed, the sequential fraction of your code, called f, creates an inescapable maximum speedup of 1 divided by f. If 10% of your code is sequential, your maximum speedup is 10, even with 1,000,000 processors. Gustafson's law counters this by exposing a flaw in Amdahl's assumption. In practice, engineers scale the problem size W up as processor count grows. The serial work remains constant, but the parallel work expands. Parallel systems allow engineers to utilize massive processor arrays, solving exponentially larger datasets in the same window of time where a single processor would stall. We can see this strict mathematical theory physically realized in modern silicon. A central processing unit uses a few heavyweight cores optimized for low latency. A CUDA-enabled graphics processing unit abandons low latency in favor of thousands of lightweight cores optimized for high throughput. If you step inside the GPU device architecture, the primary processing unit is the streaming multiprocessor, or SM. Inside the SM, the hardware warp scheduler groups threads into a warp, the fundamental execution unit. A warp consists of exactly 32 threads executing the exact same instruction simultaneously, an architecture known as single-instruction multiple threads. But having 128 CUDA cores per SM is useless if data fetching stalls your execution warps. To prevent this, CUDA relies on a strict 5-tier memory model. The two fastest memory tiers sit on chip, directly inside the SM. Registers provide thread-private storage with zero latency, and shared memory acts as an extremely fast, block-scoped communication channel for cooperating threads. The off-chip tiers are drastically slower. Constant memory is read-only and cached, while global and local DRAM suffer from massive latencies, taking up to 800 clock cycles to retrieve a single array value. To map software onto this hardware, CUDA uses a 3-level hierarchy. The overall execution grid contains multiple thread blocks, and each block contains individual threads. To map a single software thread directly to its physical hardware data, you must calculate its unique global identity. The one-dimensional index formula is index equals blockIDX.x multiplied by blockdimension.x plus threadIDX.x. CUDA programming requires precise choreography of memory, forcing warps to use coalesced global reads and maximizing shared memory to mask the 800-cycle latency of physical DRAM. The final layer of the stack is algorithmic deployment, taking theoretical logic and executing it across thousands of physical data center nodes. A traditional sequential merge sort is a divide-and-conquer algorithm with a time complexity of order n log n. It works well on a single processor, but the single thread becomes a bottleneck at scale. The parallel version maps the array onto a binary tree. During the top-down split phase, the root processor divides the data in half, passing subsets to child processors, stepping down until every leaf node holds a single element. The failure point occurs during the bottom-up merge phase. If your parallel processors utilize a standard sequential merge function to combine the arrays, that final root-level operation takes order n time, erasing the speedup you gained. The solution is to deploy a parallel merging algorithm at every single level of the tree. By doing this, the total parallel execution time plummets to order log squared n. We see the same structural requirement in graph algorithms like parallel breadth-first search. The fundamental parallelism here is that all nodes at the same level of the search tree are completely independent of each other and can be processed simultaneously. But there is a catastrophic risk in shared memory. Multiple parallel threads might discover the same unvisited target node at the exact same time. Both threads read its status as unvisited, both mark it visited, and both add it to their queues, duplicating work. To prevent this, your algorithm must use an atomic compare and swap operation. This hardware-level lock ensures that even if 1,000 threads check a vertex simultaneously, only one thread successfully claims it. Standard software loops fail at this scale. Algorithms must be mathematically restructured into logarithmic tree topologies and shielded by atomic hardware locks to survive execution on parallel arrays. The entire HPC stack functions as a singular pipeline. Network topology minimizes physical hops. Gustafson scaling dictates your problem size. CUDA memory mapping hides hardware latency, and your algorithms flatten bottlenecks to order log squared n. Because the system is entirely deterministic, exam outcomes are highly predictable. The most heavily tested problem is the 8-node prefix sum computation. There is a specific analytical shortcut here. Given an initial state of nodes carrying the values 1 through 8, the final prefixed sum results in the mathematical sequence of triangular numbers 1, 3, 6, 10, 15, 21, 28, 36. This 8-number sequence serves as a mathematical proof, allowing you to retroactively verify the manual 3-step derivations required during the exam. Memorize these specific hardware architectures, lock in the cost and index formulas. Be prepared to draw the hypercube and the CUDA memory maps. Execute those steps and you have reverse engineered the perfect high-performance computing score.